In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe. Our infinite universe is brimming with strange, violent, and potentially life-transporting phenomena. Imagine cosmic portals where objects could disappear, be ejected, or escape to some other place in space or time.
They are tickets to oblivion, for the most part. Either you get shredded in a black hole, you get transported to another part of the universe in a wormhole, or you get obliterated by the gusher of a white hole.
Blast off to the warp side of the universe as scientists search for black holes, white holes, and wormholes. Are they frivolous fantasies or a science fact? The universe is a cosmic cornucopia of endless possibilities. Imagine a shuttle service to anywhere in the cosmos. It's not aboard a futuristic spaceship. It's a galactic ride through a wormhole, a theoretical tunnel providing shortcuts through space and time.
Wormholes are a little bit like a subway system that you might use in the city, where you're going into a hole, you go through a tunnel, and then you come out at the other end through another hole, and then you've traveled through the city. The same thing would be possible in a wormhole to travel between different points in the universe.
Physicist Clifford Johnson has contemplated the possibility of wormholes.
The difference between a wormhole and a subway system is that you're using the wormhole to travel a greater distance than you would if you were traveling in ordinary space.
In theory, a wormhole has a throat connected to an entrance and exit called mouths, located in different parts of space.
A wormhole is appealing because we're limited by the speed of light. We can't get to the Andromeda galaxy in less than something like 600,000 years, even moving at the speed of light.
I keep wondering if the really next big discovery in astronomy could be a wormhole. Not just because they're fun for people like me, but because they could take us to some place that we can't plausibly ever get any other way.
Gregory Benford has pondered the science and fiction of outer space. As both a physicist and author of over 30 sci-fi novels, Benford has witnessed fantastical theories become a reality.
A lot of us would like to know if wormholes really exist or whether they're just another mathematical construct thought up by Einstein the genius.
Albert Einstein's general relativity laws allow for the existence of wormholes. In 1930, Einstein and his colleague Nathan Rosen calculated the mathematics of one of these intergalactic pipelines. It became known as the Einstein-Rosen bridge.
A wormhole is a solution of Einstein's equations for general relativity, telling us how gravity works. They're hypothetical, and what they do is they connect different parts of space and time.
The Einstein-Rosen mathematical wormhole arose from studying black holes. A black hole is a region in space of extremely strong gravity. The gravity is so strong that there is no way for objects that get too near to break away from its gravitational pull. Nothing can escape a close encounter with a black hole, not even light.
This inverted fountain serves as a visual analogy to what's going on around a black hole. At the bottom is the area inside the event horizon. and the water falling into it is analogous to gas that might fall into a black hole. Imagine yourself being a fish swimming around this region. Once you get down inside this central portion, you're past the point of no return.
But Einstein never intended his wormhole as a tool for space travel. His wormhole is theoretically created at some moment of time. It opens up briefly, then pinches off. Anything that tries to pass through it will get crushed when it squeezes apart.
The typical wormhole that you write down in your equations and study is unstable. It'll vanish in an incredibly short time. So what you need is some means of holding it open.
After Einstein's wormhole was determined unstable in the 1960s, little research was done on the concept. Then, the sci-fi film Contact was released in the late 1990s. Based on the book by renowned astronomer Carl Sagan, it proposed that a wormhole could be used for space travel.
The book Contact and then subsequently the movie was a nice place in fiction that was accessible to everyone, where you could see the idea of a wormhole. So it was a nice way of getting people interested in that idea all over again.
This was kind of a very far-fetched idea that wasn't even considered very seriously by many physicists until Carl Sagan decided to write this book and try to make it as realistic as possible. And since that time, theoretical physicists studying Einstein's general theory of relativity have considered travel through wormholes.
Scientists began to investigate whether there might be a type of wormhole different from Einstein's that is traversable. But traversable wormholes needed something to prevent them from pinching off.
You want to stabilize the wormhole. You don't want the wormhole to collapse. Keep the wormhole open. That requires something new called negative matter or exotic matter. We've never seen negative matter before. It would have anti-gravitational properties. But one day, if we ever find negative matter, perhaps that's the key to stabilize the wormhole.
The idea of a traversable wormhole captivated science fiction enthusiasts. It also reinvigorated the serious study of wormholes within the science community.
This transversable wormhole created quite a sensation, because perhaps it is physically possible to one day build a subway system to another galaxy.
The term wormhole came from an analogy with an apple. You want to get from one part of the apple to another part. If you're a worm, you can eat your way down into the body of the apple and make a little tunnel and come out the other way, and it's shorter. But unlike a worm moving here on this apple, for a wormhole in our universe, we might not know what dangers lie at the other end of the wormhole.
The other end of a wormhole could be connected to a very dangerous part of the universe, with all sorts of exotic phenomena. It might even be in the core of a star.
If we ever find a wormhole, and if it's close enough for us to reach, almost certainly we'll first send automated probes through and direct them to come back, maybe even put them on a cable in case something nasty happens to them and they can't return.
Physicists do not know of any way that a wormhole might arise naturally in our universe. But can they be made artificially?
One possibility that physicists have speculated about that might allow you to construct wormholes would be to blow them up from what's considered to be the fabric of space-time that might actually contain tiny wormholes seething in and out of existence due to the laws of quantum mechanics.
Scientists proposed that perhaps traversable wormholes could be sculpted out of quantum foam, a subatomic bubble-like structure that might exist everywhere in the universe, on length scales 1 billion trillion times smaller than the nucleus of an atom.
That's how you do it in principle. It's completely unfeasible using any technology that we know of, but it's at least something you might consider.
If one could be engineered or located in space, scientists contemplated other possibilities for a wormhole. Could it transport galactic vacationers to different points in time, as well as different places in space?
To actually create a time machine or a wormhole machine that would take us to a distant galaxy, you would have to have the physics of an advanced civilization. A civilization perhaps millions of years beyond ours.
Time machines have mystified movie audiences for over 50 years.
Gentlemen, I am talking about traveling through time in a machine constructed for that very purpose.
But could a wormhole be used for such travel?
The wormhole may lead to things like being able to go to another galaxy by walking 5 feet through a wormhole, or even going to another time.
But wormholes as time machines pose unsettling questions. In the distant future, will Earthlings be able to travel to the past and perhaps change history? Scientific ideas considered far-fetched today could one day become as acceptable as the fact that the Earth is round. The laws of physics may allow for the existence of wormholes, tunnels providing shortcuts through space as well as time. So, could these cosmic subway systems theoretically be engineered into time machines? Einstein's general relativity laws reveal that time travel into the future is possible. They show that time is perceived differently depending on where one is in the universe and how one moves. Objects moving at close to the speed of light age slower than static objects. And objects near a gravitating body age more slowly than objects farther away.
Clocks run at different rates in different gravitational fields. The stronger the gravitational field, the more slowly time passes relative to someone out in space where there's no gravitational field. On Earth here, on the surface, our clocks run slightly more slowly than clocks high up in the sky. So an example of this is that the clocks in the GPS system of satellites run a little bit more quickly than the clocks here on Earth because they're in a weaker gravitational field. And the scientists and engineers developing the GPS system had to take into account the different rate at which clocks run. If they hadn't done that correctly, then your GPS system wouldn't work. If you were taking a trip from Los Angeles to New York, you'd end up somewhere in Massachusetts.
Forward time travel has been tested using highly precise atomic clocks. Scientists have placed one clock on the ground and another in a rocket flying high above the Earth. The two were compared using radio signals between rocket and ground. The clock on the rocket ticked faster.
Here on Earth, my clock is running more slowly compared to someone in a rocket ship somewhere further away from Earth. So their clock is moving more quickly, they're going to the future faster.
Physicists have studied whether wormholes could provide travel not only to the future, but also to the past. If there was a wormhole with one mouth near Earth and the other in the center of our galaxy, the rate of flow of time will be different at the one mouth than at the other, when compared through the external universe. But when looking directly through the wormhole, the rate of flow of time appears to be the same. This difference in their relative ticking rates, as viewed externally versus viewed through the wormhole, would convert the wormhole into a time machine. What that means is that by entering a wormhole, you could leave here today and come out the other end of the wormhole hundreds or thousands of years earlier.
The wormhole may lead to things like being able to go to another galaxy, or even going to another time. It's possible you can use a wormhole of a certain kind to actually transport information backward in time, or people backward in time.
But backward time travel raises disturbing paradoxes. Could one actually voyage to the past and change history?
One of the problems with traveling backwards in time is that it produces various paradoxes. The most famous of this is the grandfather paradox. This says that if I have a time machine, I could go back in time and I could kill my grandfather, who would then never have had my father, who would never have had me, I would never have been born. So that means you would never have been able to go back into the past in the first place.
Or, let's say you go backwards in time and meet your teenage mother before you're born. And then your teenage mother falls in love with you. Then how can you be born if your teenage mother spurned your father and fell in love with you instead? The practical problems are enormous. But one day, if somebody knocks on your door and claims to be your great-great-great-great-great-great-great-granddaughter, someone from the future going backwards in time to meet her illustrious ancestor, don't slam the door. Perhaps in the future, our descendants will have the possibility of time travel, and perhaps one day they may come knocking on your door.
Backward time travel has ignited a myriad of science fiction scenarios.
If that machine can do what you say it can, destroy it, George, before it destroys you.
If the laws of physics permit wormholes, then how can those laws deal with the danger of changing history?
One possibility is that the laws of physics allow you to do backward time travel as long as it leads to a self-consistent universe, that in some sense the history is not changeable. You can't go backwards and change things, which would stop you from having been created in the first place, for example, in the grandfather paradox.
For now, forward or backward time travel through a wormhole remains in question, and some scientists think that any attempt to create a wormhole time machine may destroy the wormhole.
What actually happens when you try and make that wormhole into a time machine is that as soon as it starts connecting different times, you get a pileup of radiation so intense that it destroys the entire wormhole, thus stopping you from making that wormhole into a time machine. This seems to be a sign that maybe this is the way nature protects itself, using the laws of physics, from ever producing paradoxes and strange things that time machines seem to suggest.
Wormhole travel is really iffy because you have to know a lot about the wormhole so that it doesn't do unpleasant things like, for example, turn you into a big ball of gas all of a sudden. Because the gravitational stresses that support the wormhole are plausibly quite strong.
The idea of a wormhole is not something that we can point to and say that's impossible. It would be absurd to say we can't do that ever, because we're dealing with powers, energies, and knowledge that are outside of our current domain.
Like a wormhole, there's another phenomenon that has never been discovered. But Einstein's general relativity laws allow for its existence. It's called a white hole.
while a black hole is an object into which things are falling and disappearing, rather like a sinkhole, a white hole is doing the opposite. Things are coming out. Things are coming out rather like a fountain.
A white hole is like the unicorn, an exotic animal that's never been seen before. A white hole is very similar to a black hole, except it runs backwards. Think of running the videotape backwards. Instead of matter falling into the event horizon, never to come out, matter falls out of a black hole. So it's the opposite, a time-reversed black hole.
Black holes, as we know, have now been understood to be out there in our universe, and so you might wonder whether the same thing's true about white holes as well. For example, quasars, when they were first discovered, were thought to be maybe white holes. Why? Because they seem to be producing a huge amount of energy. We now know that that's not the case. Quasars are actually powered by black holes.
There's a school of thought that says that anything that can exist must exist somewhere. And if one adopts that school of thought, then at the moment we have to admit that white holes might be out there somewhere.
If nature uses white holes, physicists speculate that they could have been an important element in the earliest stages of the universe, maybe even in the formation of the universe itself. When trying to decode some of the mysteries of the universe, the answers may truly be black and white. The universe began with the Big Bang, an expanding fireball of matter and energy that started compressed as a tiny subatomic point called a singularity. A singularity is a region where gravity is immensely strong. The Big Bang singularity gave rise to the entire universe, which includes space, time, and all the matter that fills it. A similar type of singularity is a white hole, a theoretical object that arises in Einstein's theory of gravity. It's essentially a black hole in reverse, a point of singularity where matter is ejected. Consequently, some scientists have wondered if the universe could have been created from a white hole.
One idea to describe the entire universe has been that it's one big white hole in which there's an emergence from some initial singularity. That creative thought is one amongst many for how the universe was seeded and how it began and how the Big Bang emerged.
Think about it. A white hole emits matter. It doesn't gobble up matter. But isn't the Big Bang the same thing? That small little quantum dot that expands and spews out matter? So perhaps the white hole could be the story of our universe.
NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, has measured the radiation left over from the very early universe. Studies of this cosmic microwave background have confirmed that the universe began with a brief but colossal growth burst called inflation that preceded its regular phase of expansion. So some scientists speculate whether a white hole could have been the instigator of this growth birth.
The evidence coming from our space satellites like the WMAP orbiting the Earth right now is consistent with the idea of a multiverse. A multiverse consists of many universes like soap bubbles floating in a bubble bath. In a bubble bath, we have bubbles popping into existence, collapsing back, giving birth to baby soap bubbles. So in other words, Big Bangs could be happening all the time. Perhaps each Big Bang starts with a white hole that then expands rapidly, giving us a baby universe.
It's still unproven whether multiple universes exist, and whether white holes may have created them. But scientists have shown that some types of white holes, although possible in theory, are highly unstable. They would not survive for very long, and they simply collapse to form black holes.
Possibly white holes played a role. Perhaps they formed for a very short time, but then being unstable they collapsed. But even during that period when they were first formed, they may have left some important imprint on the future of the universe. We don't know whether that's true, but it's a possibility.
White holes are a nice act of imagination, but I don't think they have any substance yet. They're entirely theoretical objects, but then black holes were that way once upon a time.
White holes might or might not have existed at the beginning of the universe. But one thing's certain, black holes are no longer science fiction. They're science fact. Scientists agree these whirling vortexes are born out of the death throes of massive stars. When a sufficiently massive star runs out of fuel, it is unable to support itself against its own gravitational pull. It then collapses inward to form a black hole.
Black holes are troublemakers in the evolution of the universe. They can draw matter in, spew it out, reform, reorganize regions of the universe, perhaps part of a galaxy, take up residence at the center, start running the show. They're big muscular things that lumber around and cannot be stopped.
Black holes are difficult to detect because they're black. But they can be observed when they interact with something in space, such as in falling gas, which heats up and glows in X-rays.
Years ago, black holes were considered to be impossible. We have something called the giggle factor in physics. People used to giggle whenever we talked about black holes. But now we see hundreds, thousands of glorious photographs of black holes.
There are at least two types of black holes. One is called a stellar mass black hole, which is approximately 3 to 30 times the mass of our Sun. It's speculated that 100 million of these reside in our Milky Way galaxy, and similar numbers in other galaxies. The other is a supermassive black hole that is millions to billions of times the mass of our Sun. It's believed that this humongous monster lives at the center of most every large galaxy. Our own Milky Way galaxy has one. Yet whether they're stellar mass size or supermassive, all black holes are cosmic cannibals.
A black hole, in some sense, is like a cosmic roach motel. Everything checks in, but nothing checks out. A trip to a black hole would be fantastic, almost psychedelic. It's like having a near-death experience. As you get even closer to the black hole, tidal forces begin to stretch your body apart so that the top of your body and the bottom of your body experience different gravitational forces, and you become spaghettified. Eventually, even the atoms of your body become noodles and become ripped apart.
In the case of a supermassive black hole, the process of spaghettification is somewhat different. The person jumping in wouldn't be spaghettified until passing through the event horizon. And the reason for that is because the tidal forces that would stretch him aren't strong enough until you get closer to the singularity. So the person jumping in would have a few moments of perception that they were inside of a black hole, and they could marvel at that idea before they plunged toward the singularity and then became spaghettified.
And if one black hole isn't violent enough, try two black holes dueling for dominance. In the vastness of space, black holes occasionally pair off. It may appear as though they're engaging in some sort of cosmic courtship. But these unions are anything but harmonious. When two black holes get too close, they become trapped by each other's gravity. The two orbit around each other like whirling dervishes. These binary black holes will eventually collide and coalesce.
It's believed that collisions between black holes will be quite common. They would be in orbit around each other and then spiral inwards, and at some point they would coalesce. And that coalescence creates a huge disturbance in space-time.
If you have two objects that are bending space a lot around them, and they merge together, then you'll get this ripple, this wave going out, carrying energy with it.
Typically, when black holes collide, they create wild vibrations called gravitational waves, which spread across the fabric of space and time.
These ripples would be just like the ripples you would have, say, on the surface of a pond. If you threw a pebble into a pond, it creates a disturbance, and then you see the ripples carrying that disturbance away to far points of the pond.
In the past, binary black hole collisions were impossible to identify. Now, scientists have developed gravitational wave detectors to track these vibrations and hopefully catch black hole collisions in the act. LIGO is a ground-based observatory that's currently searching for gravity waves produced from collisions involving stellar-sized black holes, a few times the mass of our Sun. The system uses lasers to measure the motions of mirrors that hang by wires from overhead supports.
When two black holes merge together, they'll release these gravitational waves, these ripples in the shape of space. And as the ripples pass by these giant contraptions, they alter ever so slightly the distances between these detectors, and the detectors can actually monitor and see that change in distance. And that's the signature of a gravitational wave coming by.
In the future, LISA, a joint NASA and European Space Agency mission, will be able to detect waves from collisions involving supermassive black holes. These impacts occur after two galaxies have merged, and their supermassive black holes sink to the center of the newly formed galaxy and find each other. And if collisions involving two supermassive black holes isn't chaotic enough, try three. In January 2007, US and European satellites actually observed black hole triplets 10 billion light years away in the Virgo constellation. They're actually three quasars, which are luminous objects thought to be powered by supermassive black holes located in the centers of galaxies. This trio is in close proximity to one another. They're only about 100,000 to 150,000 light years apart, which is about the width of our Milky Way. In all probability, the three will eventually engage in a hostile merger.
If you take three large black holes brought close together because two big spiral or elliptical galaxies have slammed together, then it's a real free-for-all. And two of them could win the game and throw the third one out.
Gravitational interactions between three bodies can lead to the ejection of one of the supermassive black holes from the system. And then you're just left with a binary supermassive pair that will coalesce ultimately. The supermassive black hole that gets ejected is ejected typically with enough speed that it can't carry stars with it. So it becomes a rogue black hole. It's off on its own.
Modern science continues to unravel the mysteries surrounding black holes. But for some, one enduring question remains.
The deepest question in all of black hole physics is what lies on the other side of a black hole? What happens if you throw the encyclopedia into a black hole? Is all that information lost? We don't know for sure.
According to Einstein's general relativity laws, nothing can ever come out of a black hole. But if a black hole is extremely tiny, the laws of quantum mechanics merge with the laws of general relativity. Quantum mechanics governs the world of the very small, such as electrons, neutrons, and other subatomic particles. General relativity rules the world of the very large, where ordinary gravity is dominant, like planets, stars, and galaxies.
The fact is, when you put together quantum theory with black holes, you find that they aren't completely inert objects that only suck things in and nothing comes out. They actually radiate.
The black holes that radiate are called mini black holes, which are much smaller than their stellar mass or supermassive black hole cousins. Celebrated physicist Stephen Hawking proposed that if mini black holes exist, they must emit radiation, which has been named Hawking radiation. It is believed this radiation will cause a tiny black hole to evaporate and potentially disappear. Hawking gave mathematical evidence that when a tiny black hole forms and then evaporates, some of the information that went into the black hole never comes back out. This startling prediction caused a firestorm among physicists because the laws of quantum theory insist that information can never be completely destroyed.
Essentially, the world split into two camps. Those who believed that Hawking's calculation was really it, and the other camp that said, well, Hawking's calculation needs refining. String theory and other theories seem to suggest that the information is actually preserved. It just comes out very subtly.
The question of what happens to the information that goes inside a black hole is, I think, not fully settled. The chemical composition of the objects that went into the black hole and other aspects of them, their color, their temperature, etc., etc. We don't really know what happens to that information.
It appears unlikely that scientists could venture inside any black hole and return back home in one piece to report their findings. But a worldwide collaboration of scientists may be on the verge of the next best thing: manufacturing tiny black holes right here on Earth. Today, scientists are pushing back the boundaries of cosmic research. If naturally formed black holes aren't scary enough, what about a black hole factory? In Switzerland, at the physics laboratory called CERN, scientists have built the Large Hadron Collider, the biggest, most complex science experiment ever constructed. It's a particle accelerator, 17 miles long and the weight of 5 jumbo jets. It's capable of crushing subatomic particles together to replicate the energies that existed microseconds after the Big Bang. This particle collider was designed and built to study important questions in fundamental particle physics. But it will cram so much energy together that if physicists are lucky about how nature works at those energies, it could also produce tiny black holes.
We might be able to see microscopic black holes being formed in these high-energy collisions, and those black holes would then be amenable to study. They would rapidly evaporate. We'd be able to study their decay products and understand physics of quantum gravity in the laboratory, which is something that we never dreamed we'd be able to do in our lifetimes.
But the possibility of manufacturing mini black holes has roused suspicion and fear. Could they escape the Earth's gravity and eventually devour our planet?
Cosmic rays from outer space hit the Earth all the time, perhaps with more energy than these mini black holes. So these mini black holes are harmless. They're not going to eat up the Earth. They are not a doomsday device.
A similar mini black hole scare happened in the United States. In Brookhaven, New York, a smaller collider experiment is already underway. The relativistic heavy ion collider, better known as RIC, is an underground pipeline where gold atoms collide together at 99.9% the speed of light. When the experiment began in the year 2000, news spread that these head-on impacts created black holes.
The laboratory, which is very responsible, decided it needed to respond to this and reassure people, so it convened a group to look at this. And what that group found was that these kinds of collisions had been happening in outer space, and that had never caused a problem. Theoretically, we produce conditions in these collisions which should mathematically give some similarity to the theory that surrounds black holes. But in practice, we're completely safe. There's no way that any black hole that could be a concern could be produced here at RIC.
Well, RIC certainly is not capable of producing a black hole of any kind. There is not enough mass which is being created here by many orders of magnitude.
Although RIC cannot create mini black holes, scientists can go through the ashes of these particle collisions to learn about the early moments a few microseconds after the Big Bang.
So we can use this knowledge to gain a better understanding of what happened shortly after the Big Bang, including the possibility of primordial black hole formation.
The particle collision experiments in Switzerland and in the US may not produce life-threatening black holes, but they could give several important clues about whether information comes back out of a mini black hole and even how the universe began.
They do provide a laboratory to see how far we can push Einstein's theory until all hell breaks loose and the equations collapse. And that's why we think that mini black holes could be a key to going beyond Einstein.
Physicists will continue to probe into the mysteries still surrounding black holes. They will also remain on high alert for any signs of the elusive wormholes and white holes. The search for the next frontier marches on.
White holes, wormholes, black holes are tickets to oblivion for the most part. None of these are places that you want to take your summer vacation near. And these tickets will cost a lot to even find. These objects are hard to observe in the universe, and only one of them do we really pretty much know is there, the black hole. The others may be entirely hypothetical. They may be the unicorns of astronomy.
There are several cases in history of science when an idea or even a solution to an equation just seemed like an artifact of our imaginations and it actually turned out to be a real thing. Black holes are such an example. Maybe white holes and wormholes will have some role in nature which we'll one day discover.